Imagine standing beneath a night sky, gazing up at the countless twinkling stars. They seem eternal, unchanging, yet each one is undergoing an extraordinary journey. A journey that spans billions of years, from fiery birth to dramatic demise. Some stars burn bright and die young, while others linger for eons, shaping the very fabric of the universe. They forge the elements in our bodies, scatter light across the cosmos, and sometimes explode in spectacular finales that outshine entire galaxies. Stars are the ultimate cosmic storytellers, and thanks to breakthroughs in astrophysics, we can now read their stories like never before. We can predict their fates, anticipate their transformations, and even estimate how long our own sun will continue to shine before it meets its inevitable end. But what if I told you that not all stars fit into the categories we've come to understand? What if, lurking in the vastness of space, there exist stars unlike anything we have ever seen? Today, we are venturing beyond the familiar, beyond the stars we recognize. We're exploring the realm of the exotic, the hypothetical, and the almost mythical. The kinds of stars that shouldn't exist, yet might. These bizarre celestial objects defy the known laws of physics, stretching our understanding of the universe to its limits. Some may mimic black holes, some could be composed of dark energy, and others might challenge our very definition of what a star is. Could these mysterious objects already be hiding in plain sight, misidentified as something else? Could they be the key to answering some of the greatest mysteries in astrophysics? Join me as we embark on a journey through the strangest stars in the universe. A journey that will take us from the familiar glow of our sun to the eerie darkness of theoretical objects that may exist beyond our wildest imagination. At the heart of every star lies a cosmic struggle between two immense forces: gravity and pressure. This is the fundamental battle that dictates a star's lifespan, structure, and eventual fate. Gravity is relentless, pulling all the mass of a star inward, trying to crush it into the smallest possible space. If left unchecked, this gravitational collapse would shrink the star into an impossibly dense singularity. However, the reason stars don't collapse immediately is because of an opposing force: internal pressure. This pressure originates from the immense energy produced by nuclear fusion at the star's core. Inside a star like our Sun, hydrogen atoms collide and fuse into helium, releasing an extraordinary amount of energy in the process. This energy, emitted in the form of radiation, exerts an outward radiation pressure that counteracts the force of gravity, preventing the star from collapsing under its own weight. This equilibrium between gravity and outward pressure is known as hydrostatic equilibrium, a delicate balance that allows stars to shine steadily for billions of years. The type of fusion occurring within a star depends on its mass and stage of evolution. In smaller stars, the fusion process primarily involves hydrogen atoms merging into helium. As stars evolve, heavier elements, such as carbon, oxygen, and eventually iron, are formed through successive fusion reactions. This nuclear alchemy not only fuels the star, but also dictates its fate. For stars significantly larger than our Sun, the battle between gravity and pressure becomes even more intense. These massive stars burn through their fuel much more rapidly, generating enormous amounts of energy. However, when they exhaust their nuclear fuel, gravity inevitably wins, leading to their dramatic demise as supernovae, neutron stars, or even black holes. On the other hand, stars much smaller than our Sun, such as red dwarfs, burn their hydrogen at a much slower rate. Some of these low-mass stars are predicted to shine for trillions of years, making them some of the longest-lived objects in the universe. Unlike their massive counterparts, these stars will quietly fade away into white dwarfs, without a cataclysmic explosion. Understanding this battle between gravity and pressure helps explain why stars follow distinct life cycles and why some end in spectacular fashion while others quietly fade away. But what happens when this balance is disrupted? In the case of exotic stellar objects, new forces can come into play, creating bizarre and hypothetical stars that challenge our understanding of physics. What happens when this balance breaks? But stars don't last forever. Eventually, they run out of fuel. When fusion slows down or stops, the outward pressure drops and gravity takes over. What happens next depends entirely on the mass of the star. For small stars like our Sun, up to 1.4 times the mass of the Sun, fusion will eventually stop, and the star will shrink into a white dwarf. These incredibly dense remnants are held up by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed into the same space. For larger stars, between 1.4 and 2.2 times the Sun's mass, electron degeneracy pressure isn't strong enough to prevent collapse. The core shrinks even further, forcing protons and electrons to merge into neutrons. This forms a neutron star, a city-sized celestial object so dense that a sugar cube-sized portion of it would weigh 1 billion tons on Earth. For the most massive stars, above 2.2 solar masses, not even neutron degeneracy pressure can stop gravity. The core continues to collapse until it becomes a black hole, an object so dense that not even light can escape its gravitational grip. One of the most critical thresholds in astrophysics is the Chandrasekhar limit, named after the Indian physicist Subrahmanyan Chandrasekhar. This limit, 1.4 times the Sun's mass, marks the maximum size a white dwarf can be before it collapses into a neutron star. Similarly, neutron stars have their own limit, the Tolman-Oppenheimer-Volkoff limit, around 2.2 times the Sun's mass. If a neutron star exceeds this mass, it will continue collapsing until it forms a black hole. But what if something even more exotic exists? Could there be a new form of matter beyond neutrons? One that prevents total collapse? Imposter, the notion of black holes is among the most accepted ideas in astrophysics. We have observed their indirect effects, measured their gravitational influence, and even captured an image of their event horizon. But despite all this, black holes still pose an unsettling paradox. The concept of a singularity, where matter collapses into an infinitely dense point, defies our current understanding of physics. What if there is an alternative? What if some black holes aren't black holes at all? This is where the gravitational vacuum star, or Gravastar, emerges as a fascinating alternative. First proposed in 2001 by Mazur and Motola, the Gravastar model suggests that instead of a singularity hidden behind an event horizon, what we perceive as a black hole might actually be a star-like object composed of vacuum energy. Vacuum energy is a concept from quantum field theory, a mysterious, repulsive force that might be responsible for the accelerating expansion of the universe. If such energy could be concentrated within a collapsing star, it could counteract gravity in a way that prevents the formation of a singularity. In other words, rather than becoming a black hole, a collapsing star could stabilize into an exotic object, a gravastar. The structure of a gravastar is unlike anything we have seen before. Its outer shell, an ultra-thin yet incredibly dense layer, holds back an interior filled with vacuum energy. This balance creates an object that outwardly resembles a black hole but lacks a singularity. More intriguingly, because there is no event horizon, information and radiation might still be able to escape, offering a theoretical way to distinguish gravastars from black holes. But how could we tell if a black hole is actually a gravastar? Observationally, it's difficult. Both objects would appear almost identical to an outside observer. However, recent studies suggest that gravitational wave signals from merging objects could hold clues. If gravastars exist, their mergers might produce different wave patterns than those from true black holes. Advanced instruments like the Laser Interferometer, Gravitational Wave Observatory, LIGO, might eventually help us solve this mystery. The existence of gravastars would revolutionize our understanding of astrophysics, forcing us to rethink fundamental principles of relativity and quantum mechanics. Some even speculate that gravastars could be linked to dark energy, or be gateways to entirely new realms of physics. Are they real? We don't yet know, but as our observational techniques improve, we may one day discover that not everything we call a black hole is truly a black hole after all. The universe, as always, remains full of surprises. Black holes have long been considered the ultimate fate of massive stars. Their presence confirmed through gravitational interactions, X-ray emissions, and even direct imaging. Yet, at their core lies an unsettling paradox. A singularity where matter is thought to collapse into an infinitely small, infinitely dense point. This defies our understanding of physics. What if, instead of collapsing into a singularity, something else happens? Enter the gravitational vacuum star, or gravastar, a concept proposed in 2001 by physicists Pavel Mazur and Emil Motola. Instead of an event horizon surrounding a singularity, gravastars might be composed of an exotic form of vacuum energy, creating an object that looks like a black hole from the outside, but is fundamentally different on the inside. If gravastars exist, they could solve one of the most troubling issues in modern astrophysics: the information paradox. In a traditional black hole model, anything that falls inside the event horizon is lost forever. Quantum mechanics, however, suggests that information cannot be destroyed. Gravastars offer a potential way out. Since they do not have event horizons, they may allow information to escape over time. But how could we detect one? That's the tricky part. From a distance, a gravastar and a black hole would appear nearly identical. The real test would come in high-energy astrophysical events, such as the collision of two massive objects. Gravitational wave data from LIGO and Virgo suggest that some detected events may not match what we expect from black hole mergers. Could these anomalies be signs of gravastars? Another possibility lies in their interaction with surrounding space-time. Unlike black holes, which completely absorb all incoming matter and light, gravastars might scatter some radiation back out. This could produce subtle differences in the way they emit X-rays or interact with surrounding gas clouds. Future space telescopes and deep space observatories may provide the key to identifying them. If gravastars do exist, they could have profound implications for our understanding of not just black holes, but also dark energy. Some theories suggest that vacuum energy inside Gravastars might be related to the mysterious force driving the accelerated expansion of the universe. Could studying these objects help us unlock the secrets of dark energy? The search for Gravastars is just beginning. As our technology improves, new observational techniques could finally confirm or refute their existence. If they are real, they may reshape everything we know about the most extreme objects in the cosmos. For now, they remain one of the most tantalizing mysteries in modern astrophysics. Betelgeuse, a red supergiant star located in the Orion constellation, has long fascinated astronomers. As one of the closest massive stars to Earth, it provides a rare opportunity to observe the final stages of stellar evolution in real time. However, Betelgeuse has been behaving in ways that challenge our understanding of how supergiant stars operate. Recent observations have revealed that Betelgeuse is spinning much faster than expected for a star of its size and age. Normally, a star as massive as Betelgeuse should have slowed down over millions of years due to its massive stellar wind and expansion into a supergiant phase. It appears to be rotating at an astonishing speed, far beyond what theoretical models predict. Could it have gained angular momentum through an unknown process? Or did Betelgeuse once have a binary companion that merged with it, transferring rotational energy? Adding to the mystery, Betelgeuse underwent an unprecedented dimming event in late 2019 and early 2020, leading some to speculate that it was about to explode as a supernova. However, the dimming was later attributed to a massive ejection of material from its outer layers, which formed a dust cloud that temporarily obscured the star's light. This unexpected behavior suggests that Betelgeuse is experiencing internal convective instability, something rarely observed in real time. The question remains, is Betelgeuse on the brink of a spectacular supernova? Or are we witnessing an entirely new type of stellar phenomenon? If it does explode, it will provide an extraordinary opportunity for astronomers to study the physics of supernovae up close. Until then, Betelgeuse continues to defy expectations, reminding us that even the stars we think we understand can still surprise us. Coronae Borealis, also known as the Blaze Star, is a celestial enigma that defies conventional stellar evolution. This extraordinary recurrent nova, located approximately 3,000 light-years from Earth in the constellation T Coronae Borealis, has intrigued astronomers for centuries. Unlike standard novas that experience a single outburst before fading into obscurity, the Blaze Star erupts at regular intervals, making it one of the rarest and most fascinating objects in our galaxy. What makes T Coronae Borealis so unique? How does it sustain its cycle of explosions? With its next expected eruption predicted for 2024, astronomers and sky watchers alike are preparing for what could be one of the most spectacular astronomical events of our lifetime. In this comprehensive analysis, we explore the history, mechanics, significance, and future observations of this enduring cosmic phenomenon. The history of the Blaze Star's eruptions. T Coronae Borealis is one of the few known recurrent novas, a class of stars that undergo repeated outbursts. Astronomers have recorded its spectacular eruptions on two significant occasions, in 1866 and 1946. The first documented explosion of the Blaze Star was observed in 1866. Before its eruption, it was a dim star barely visible to the naked eye. However, during the outburst, it surged to a magnitude of around +2, making it as bright as Polaris, the North Star. The sudden brightness startled astronomers, marking the beginning of detailed studies into recurrent novas. After nearly 80 years of dormancy, T Coronae Borealis exploded again in 1946, following a remarkably similar pattern to its previous eruption. Once again, the star brightened dramatically before fading back to obscurity. This second explosion confirmed that the blaze star was no ordinary nova, but rather a recurrent nova, a rare subclass of stellar phenomena. Based on historical data, astronomers anticipate the next eruption to occur sometime in 2024, give or take a few years. This event could provide invaluable insights into the behavior of recurrent novas and their underlying mechanisms. T Coronae Borealis is a binary star system consisting of a white dwarf and a red giant. The white dwarf is an extremely dense remnant of a once massive star, no larger than Earth, but with a mass comparable to that of the Sun. The red giant, a massive, cooler star nearing the end of its life cycle, has an extended outer envelope that gradually loses material. In this system, the white dwarf gravitationally pulls material from the red giant, accumulating hydrogen on its surface. Over time, as this hydrogen layer builds up, it reaches a critical pressure and temperature, triggering a thermonuclear runaway reaction. This sudden energy release results in a nova explosion, making the star momentarily one of the brightest objects in the night sky. Unlike supernovae, which result in the complete destruction of a star, a nova explosion does not destroy the white dwarf. Instead, it ejects excess material into space while leaving the binary system intact. Once enough new material accumulates, the cycle repeats, leading to another eruption decades later. One of the greatest mysteries surrounding the blaze star is its regular cycle of eruptions. Why does it erupt roughly every 80 years? While the exact mechanics remain uncertain, astronomers propose several key factors. The mass transfer rate, the amount of hydrogen transferred from the red giant to the white dwarf, plays a crucial role. If the transfer rate remains steady, the nova cycle should be relatively predictable. The exact mass and composition of the white dwarf also influence how much material it can accumulate before triggering an explosion. Some scientists hypothesize that magnetic fields within the binary system could regulate the transfer of material, creating a consistent eruption interval. The buildup of hydrogen and the temperature variations in the accretion disk around the white dwarf might also contribute to its cyclical nature. Understanding these variables is critical, as it can help predict not only the future eruptions of T Coronae Borealis, but also similar events across the cosmos. If predictions hold, the next eruption of the blaze star could happen any time within the next few years. When it does, it will briefly outshine many of the stars in its constellation, making it visible to the naked eye, even in urban areas with moderate light pollution. For astronomers, this is an opportunity to capture high-resolution data using advanced telescopes, spectrometers, and space observatories. Key scientific goals for the 2024 event include measuring the exact brightness profile to refine models of recurrent novas, studying the composition of the ejected material to understand the nuclear processes at work, monitoring how quickly the star fades after the eruption to provide clues about the dynamics of mass ejection and accretion, and using radio telescopes to detect any unusual emissions that might hint at previously unknown properties of the system. For amateur astronomers and stargazers, witnessing a nova explosion in real time is a rare and thrilling experience. no special equipment will be necessary. Simply looking up at the night sky at the right time could reveal a cosmic firework display billions of times more powerful than any earthly explosion. Understanding the blazed star extends beyond just one recurrent nova. Research into these celestial objects has profound implications for stellar evolution and death. As scientists can refine models of how binary systems evolve and how stars transfer mass in close stellar pairings. Some white dwarfs in recurrent nova systems may eventually accumulate enough mass to trigger a Type Ia supernova, one of the most powerful stellar explosions in the universe. By analyzing stars like T Coronae Borealis, astronomers may improve predictions for when and where these cataclysmic events will occur. Type Ia supernovae serve as standard candles for measuring cosmic distances. If we can better understand recurrent novas, we may improve our understanding of how some of these systems transition to full supernovae, refining distance calculations for galaxies across the universe. T Coronae Borealis, the blazed star, is one of the most fascinating celestial phenomena known to humankind. With its next eruption expected around 2024, astronomers and skywatchers eagerly await another glimpse of this enduring cosmic event. The study of recurrent novas like the blazed star not only sheds light on stellar physics, but also enhances our understanding of the broader universe. As we approach the next predicted explosion, scientists and enthusiasts alike will turn their eyes to the heavens, awaiting a dazzling event that has been over 80 years in the making. So, will 2024 bring another spectacular outburst? Only time will tell. But one thing is certain: the blazed star will continue to burn brightly in the annals of astronomical history, a nova that simply refuses to die. The very fabric of astrophysics rests on one critical assumption: the universe is 13.8 billion years old. This number, derived from cosmic microwave background radiation, the expansion rate of the universe, and galactic evolution, is one of the most well-tested figures in modern science. But what if I told you there exists a star that appears to be older than the universe itself? Meet HD 140283, commonly referred to as the Methuselah Star. This ancient star, located about 200 light-years away in the constellation Libra, has baffled astronomers since it was first studied in detail. Initial estimates of its age placed it at 14.5 billion years, a figure that immediately sparked controversy. If the universe itself is only 13.8 billion years old, how can a star be older than the cosmos? The Methuselah Star is a metal-poor subgiant, meaning it contains far fewer heavy elements than younger stars. This aligns with our understanding of cosmic history. Earlier stars formed from pristine hydrogen and helium, while later generations inherited heavier elements forged in supernovae. But this still leaves us with a puzzle. Is the Methuselah Star truly older than the universe? Or is there a flaw in our calculations? Some astronomers argue that even small revisions in our understanding of stellar evolution models could resolve the paradox entirely. Others suggest that the apparent contradiction might hint at unknown physics, or even the possibility that our measurement of the universe's expansion rate, the Hubble constant, is slightly off. As astronomical instruments become more precise, future observations may finally determine whether this enigmatic star is a mere miscalculation, or a sign that our understanding of the cosmos is still incomplete. The Tarantula Nebula. the most active star-forming region. Deep within the Large Magellanic Cloud, a satellite galaxy of the Milky Way, lies one of the most astonishing cosmic nurseries ever discovered, the Tarantula Nebula, 30 Doradus. This immense region of gas and dust is not just a nebula. It is the most active star-forming region known in our local universe. It's a place where stars are being born at an unprecedented rate, shaping the future of an entire galaxy. Stretching nearly 1,000 light-years across, the Tarantula Nebula is home to some of the most massive and luminous stars ever observed. At its core lies R136, a dense star cluster housing stars so enormous that they challenge our understanding of stellar physics. One of these, R13601, holds the title of the most massive star ever discovered, weighing in at a staggering 315 times the mass of the Sun. But what makes the Tarantula Nebula so extraordinary? Unlike other star-forming regions, which may host a slow trickle of new stellar births, the Tarantula Nebula is undergoing a stellar baby boom, forming thousands of new stars in a single epoch. This intense activity is driven by the nebula's high gas density and extreme radiation environment, conditions that resemble those found in the early universe when the first galaxies were forming. The nebula is also a cosmic laboratory for studying supernova explosions. In 1987, the Tarantula Nebula hosted SN 1987A, the closest observed supernova in modern times. This cataclysmic event provided astronomers with an unprecedented view of the death of a massive star, helping to refine our models of how these titanic explosions seed the universe with heavy elements. Looking into the Tarantula Nebula is like gazing back in time, witnessing the same conditions that once gave rise to stars, planets, and even life itself. As our telescopes become more powerful, this region will continue to be a gold mine of discovery, revealing the secrets of how stars are born and how galaxies evolve. SN 1987A, the closest supernova in modern history. Supernovae are among the most spectacular and energetic events in the universe, marking the explosive death of massive stars. These cosmic cataclysms release immense energy, forging heavy elements essential for life and dispersing them throughout space. In modern astronomy, few supernovae have been as pivotal as supernova 1987A, SN 1987A, which erupted in the Large Magellanic Cloud, LMC, a satellite galaxy of the Milky Way, in 2087 February 1987. It was the closest observed supernova in nearly 4 centuries and the first to be studied in real time with modern telescopes, making it a milestone in astrophysics. SN 1987. A was not only an extraordinary observational opportunity, but also a challenge to existing theories of stellar evolution. Unlike most supernovae, which arise from red supergiants, SN 1987A originated from a blue supergiant, forcing scientists to rethink the final stages of stellar life. Additionally, the supernova provided crucial insights into neutrino physics, the formation of neutron stars or black holes, and the intricate dynamics of stellar remnants interacting with their surroundings. More than 3 decades later, astronomers continue to monitor SN 1987A, as its expanding remnants reveal new details about the mechanisms governing stellar death and rebirth. The discovery and immediate impact. On February 23, 1987, astronomers Ian Shelton and Oscar Duhalde at the Las Campanas Observatory in Chile first spotted SN 1987A, followed shortly by an independent detection by Albert Jones in New Zealand. Located approximately 168,000 light-years away in the Tarantula Nebula region of the Large Magellanic Cloud, this explosion was the closest supernova observed since Kepler's supernova of 1604. Unlike historical supernova, which were observed with the naked eye or rudimentary telescopes, SN 1987A was the first to be examined with sophisticated instruments, including radio, infrared, optical, and X-ray telescopes, providing an unprecedented wealth of data. SN 1987A quickly became one of the brightest objects in the night sky, outshining its host galaxy for several months. The explosion's peak luminosity was equivalent to 100 million suns, a testament to the sheer power of supernovae. Observations across multiple wavelengths allowed scientists to analyze the physical processes occurring during and after the explosion in real time. A stellar mystery, the unusual progenitor star. Most supernovae originate from red supergiants, massive stars that have expanded and cooled in their final stages before collapsing under their own gravity. However, SN 1987A defied expectations. When scientists traced its origin, they found that its progenitor was not a red supergiant, but a blue supergiant named Sandulig, minus 69 degrees 202. This was highly unexpected, as blue supergiants are hotter and were not thought to undergo core collapse supernovae under normal circumstances. The presence of a blue supergiant as the progenitor of SN 1987A forced a reassessment of stellar evolution models. Some theories suggested that the progenitor had once been a red supergiant that shed its outer layers, contracting back into a blue supergiant before exploding. Others posited that interactions with a binary companion could have influenced its unusual evolution. Regardless of the explanation, SN 1987A demonstrated that the life cycles of massive stars were more complex than previously believed. Neutrinos, a groundbreaking detection. One of the most groundbreaking aspects of SN in 1987 A was the detection of neutrinos, nearly massless subatomic particles that rarely interact with matter. Hours before the visible explosion, several underground neutrino observatories, including Kamiokande 2 in Japan and the Irvine, Michigan Brookhaven detector in the United States, detected a burst of neutrinos. This was the first time neutrinos from a supernova had been observed directly, confirming theoretical predictions about how massive stars collapse. In total, 25 neutrinos were recorded from SN 1987A, an astonishingly small number considering that an estimated neutrinos were emitted. However, this small detection was monumental. It confirmed that supernovae release the majority of their energy in the form of neutrinos rather than electromagnetic radiation. This discovery not only validated key aspects of stellar collapse theory, but also established neutrino astronomy as a viable field of study. The expanding remnant, a cosmic laboratory, SN 1987A, has continued to be a fascinating object for astronomers, as its remnants provide insights into the aftermath of supernova explosions. The explosion expelled vast amounts of gas and dust, forming a distinctive structure that includes a central region surrounded by a glowing ring. This ring, which was formed from material ejected by the progenitor star thousands of years before the explosion, has been steadily expanding and interacting with the surrounding interstellar medium. Observations with the Hubble Space Telescope, HST, have revealed that this ring is now being illuminated and shaped by shock waves from the explosion. providing a unique opportunity to study how supernova remnants evolve over time. Additionally, the Atacama Large Millimeter Submillimeter Array, LMEA, has detected significant amounts of dust in the aftermath, supporting theories that supernovae are a major source of cosmic dust. The missing neutron star or black hole. A key question surrounding SN 1987A is what remains at its core. In most cases, core collapse supernovae leave behind either a neutron star or a black hole. However, despite extensive searches, no compact object has been definitively detected in SN 1987A. Some astronomers speculate that a neutron star is hidden within the dense debris, shrouded by dust and gas. Others propose that the explosion may have resulted in a direct collapse into a black hole, though this scenario is less likely given the observed neutrino burst. Future observations with next-generation telescopes like the James Webb Space Telescope, JWST, may finally resolve this mystery. Broader implications for astrophysics. SN 1987A has had a profound impact on multiple fields of astrophysics. Its contributions include supernova mechanics. The real-time study of SN 1987A has provided unprecedented insights into how shock waves propagate, how elements are synthesized, and how energy is distributed in supernova explosions. Neutrino physics. The detection of neutrinos confirmed core collapse supernova models and contributed to advancements in particle physics, including studies on neutrino oscillations. Cosmic dust production. The discovery of dust formation in the remnants of SN 1987A has implications for understanding the origins of dust in the early universe. Star evolution models. The unexpected blue supergiant progenitor forced a re-evaluation of stellar evolution theories, emphasizing the role of binary interactions and mass loss in shaping the final fate of massive stars. Supernova remnants, SN 1987A continues to serve as a case study for understanding how supernovae shape their surrounding environments and contribute to the chemical enrichment of galaxies. Despite being over 35 years since its explosion, SN 1987A remains an active area of study. Instruments like JWST, ALMA, and HST continue to monitor its evolution, uncovering new details about its expanding remnants. Scientists hope to eventually detect the elusive neutron star or black hole at its core and gain deeper insights into the long-term evolution of supernova remnants. SN 1987A is one of the most significant supernova in human history, offering a rare and detailed look at the life cycle of massive stars. From its unexpected blue supergiant progenitor to its historic neutrino detection, SN 1987A has reshaped our understanding of stellar death and the fundamental physics governing the universe. As astronomers continue to study its remnants, this extraordinary explosion will undoubtedly yield even more discoveries, cementing its place as a cornerstone of modern astrophysics. The universe still holds its secrets. Despite the incredible advancements in modern astrophysics, the universe continues to challenge our understanding at every turn. Each discovery leads to new questions, and every anomaly forces us to reconsider what we think we know about the cosmos. The exotic stars we've explored in this journey remind us that science is not about having all the answers. It's about continuously seeking them. From the peculiar behavior of Betelgeuse to the baffling paradox of the Methuselah Star, we've seen how even the most well-established theories can be questioned. The universe is a vast, mysterious place, filled with objects that stretch the limits of physics and force us to expand our perspective. And perhaps the most exciting part is that there is still so much left to uncover. As new telescopes and instruments come online, like the James Webb Space Telescope, we may soon find even stranger stars, hidden realms of physics, or even signs of life beyond our solar system. Until then, the cosmos remains a grand puzzle, waiting for us to solve it, one star at a time.